Okay, so in the last class we looked at discrete log problem, uh, and so that is alpha raised to x is equal to beta, where alpha and beta belongs to some discrete set. Normally we take it as a group, and in the last class we took an integer modulo p, okay, ZP, where alpha and beta belongs, and we need to find x. Okay, I gave you two algorithms to compute, although these are not very efficient algorithms, and they work when you're looking at small values, but for higher values, the problem is infeasible actually, for any group. And this problem was solved by Peter Shor in 1994 on quantum computer. So he gave first time a polynomial time algorithm for solving it on a quantum computer. Okay, so now I am going to introduce uh, one crypto system based on this discrete log, which is algorithmic crypto system. So in fact, you can take algorithmic type crypto system on any group. So there are two kind of groups which I am going to discuss briefly. Before that, I am going to use, I will show you how discrete log problem can be used uh, to communicate secret key. Okay, so normally we know that RSA crypto system is used for sharing the secret key. So suppose we are encrypting our data using DES or AES, but then we require to send a key. Okay, so how to send key? So one way is using RSA crypto system. Another way I can show you is what is known as Def-Hellman key exchange. So using that we can actually send or share the key on a public channel. Okay, so let me explain to you that. So how Def-Hellman key exchange problem work? Actually, it's something. So we have Alice or Bob, and they select a large prime P and a primitive root alpha mod P. Alpha is a primitive root, means order of alpha is P minus 1. Okay. ZP star is a group with respect to multiplication, integer modulo P star. Okay, 0 is not there. So all the elements 1, 2, 3 up to P minus 1. Total number of elements in ZP star is P minus 1. An element alpha of ZP star is said to be primitive if order of alpha is whole group P minus 1. That means you can generate the whole group using alpha. By just taking powers of alpha, you will get the entire group. Okay. So now what you do? So this is step 1 actually. Alice or Bob select a large prime P and a primitive root alpha. So both P and alpha are public. So it's a public data. You can make these two things public. Now, Alice chooses a secret random x. X lies between 1 and P minus 2. Okay. And Bob selects a secret random y. So alpha and p are known in the public domain. Now Alice will choose a secret random number x, and Bob has selected a random number, secret random number y. Okay. Now, if Alice wants to send something to Bob, so basically the objective is that they want to share a key, a common key. Okay. So now I'll show you how to basically get a common key, without actually. So we are sending something on the public channel. Even if somebody has access to those data on public channel, he or she will not be able to get any information about the secret key that is transmitted. Okay, and the reason is because discrete log problem is a difficult problem, infeasible problem. Okay, so that's why you have to choose a large prime. Everything is when you choose a large prime, more than 200 digits, and so you can make sure that it is a secret system. So let me show you after that. Next step. Step 3. Alice sends alpha is for x, alpha is for x mod p. So Alice, because x is known to Alice, right? She can compute alpha is for x mod p and send it across the public channel. And what Bob does? Bob sends alpha is for y mod p. X is known to Alice, y is known to Bob. Just compute alpha is for x mod p and then send it across the channel. So Bob will receive alpha is for x mod p. What Bob will do? Now, any idea? Once Bob will receive alpha is for x and Alice will receive alpha is for y. So how to make a common thing? Any idea? Alice sends alpha is for x, Bob receives alpha is for x, right? X, Alice, so Bob does not know what is x. Similarly, Alice does not know what is y. So it's very simple now. Once Bob receives alpha raised for x, he raises this thing power of y. And this guy will raise it to the power of x because that is known to them, right? And now they have common. I mean, they will get the common key, right? Right? So using the messages they receive, what they can do, they can calculate the session key. For Alice, key is alpha raised for y raised for x. And for Bob, right? So both will have the same key. They are not sending k, but they are sending pieces of it, right? So that you can actually now reconstruct the key, right? Now, once session key k is common, right? So there could be a protocol saying that we will take middle 56 bits of k as a key for AES or DES, right? Certain number of bits from this k, and that is enough. Okay. So this is how the session key is established. A common key is established between Alice and Bob while sending them on a public channel. Got it? Why it is difficult for anyone? So what is communicated here? Alpha raised for x or alpha raised for y is communicated on a public channel, right? Somebody knows alpha raised for x, which is nothing but beta. Finding x is nothing but a discrete log problem. Similarly, if you know alpha raised for y, which is equal to beta, finding y is a discrete log problem. So we assume that it is infeasible, okay, in whatever group we are handling. So right now here we are handling the group ZP star. ZP star is equal to 1, 2, 3 up to p minus 1. all p minus 1 elements. Got it? Here the requirement is, you remember, discrete log is well defined if alpha is a primitive root. So that assumption we have taken here, that order of alpha is p minus 1. Okay? Full thing. Got it? Any question? This is the nice step element. It's a very simple thing, yet very powerful thing, and is used, quite often. Okay. So I can actually, so whatever I've covered about discrete log in general, I can write it in the form of a group. A multiplicative group, G is given to you, suppose, and alpha is an element in this group, and order of alpha is n. And suppose beta order of alpha is equal to n. Suppose beta is a member of this cyclic group alpha generated by alpha, a group generated by alpha, which is power of alpha. Right? So the discrete log problem in terms of group can be defined. Find a unique integer a 0 less than or equal to a less than or equal to n minus 1 such that alpha is for a is equal to beta. A is nothing but defined as discrete log of beta at base alpha. So in the previous discussion, in the previous classes, I have taken z is equal to integer modulo p star, multiplicative group with respect to multiplication, right, in zp star. In general, we can define the discrete log problem for any group. What is group? You know, right? Group is a is a non-empty set together with a binary operation such that it is closed with respect to that operation, associative, existence of identity, and existence of multiplicative inverse, right? These four properties are there, right? That is it. That structure is a group. In any such group, problem is defined in a more general setting like this. Okay. Now you will see that in practice, I will talk about a curve, a special kind of curve, and look at the points on that curve on this group, some group actually. I mean, not in the group, actually, you look at the points on the curve, they form a group with respect to addition of 2 points on the curve. And that curve is known as elliptic curve. It's a very beautiful curve. I'll talk about it. So, basically you can build a crypto system based on any such group. Okay. So before giving into this idea of elliptic curve crypto system, now I'm going to, so in this general setting of groups, so I am going to again focus on ZP star to tell you something about Elgamal crypto system, how that crypto system is designed based on discrete log problem. Elgamal crypto system based on discrete log problem in ZP star respect to multiplication. ZP star is nothing but 1, 2, 3 up to p minus 1. Okay, so with respect to multiplication, they form a group. Okay. So what is this crypto system? Suppose P is a prime such that discrete log problem is infeasible in ZP star. So this assumption is very, very important, right? So that means we have to take P to be such a large prime such that discrete log problem is difficult to solve. As you know that from the previous algorithm that I showed to you in the last class, that if p is small, actually you can find the value of discrete log, right? So you need to take it enough so that for the large primes, it is difficult. Even if you write a computer program, it is going to take a lot more time, right? So it's a difficult problem, okay? So now you take alpha to be an element in ZP star. It could be any of the number 1 to p minus 1. Now we are taking alpha to be a primitive element. So order of alpha is p minus 1. So alpha is a primitive element. Okay. Order of alpha is p minus 1. Fine. Plain text is coming from ZP star in the crypto system, and cipher text is ZP star cross ZP star. Okay. Now we define key. Define A is equal to P alpha A beta such that beta is congruent to alpha raised per A not P. We can write it down again. So some problem again, alpha A beta is congruent to alpha raised per A. Okay. So here P, alpha and beta are public. Public key, public data. A is a private key. So our key consisting of 4 numbers, P, alpha, A, beta. So P, alpha and beta are known to public, right? Beta is known to public, alpha is known to public, and P is known to public because what prime we are using. A is a private key. Only A is a private key. Okay? Okay. Now I want to send some plain text, say random, So in order to send for a given k is equal to P alpha A beta, okay, and a secret random number z. Sorry, random number k in ZP minus 1. Define ek of x. X is your plain text that you want to send. K is equal to y1, y2. Y1 is alpha raised per k mod p, and y2 is x times beta raised per k mod p. So x is our plain text, k is randomly chosen number, secret random number, okay. X is our plain text. Encryption function is combining x and k. Cipher text is y1 comma y2. Y1 is alpha raised per k mod p, this k, right? And y2 is mass, so x times beta raised per k mod p. Got it? So cipher text is y1 comma y2. Pair y1 comma y2. Two numbers y1 comma y2. Where y1 is, because alpha is known to everyone, p is known to everyone, So encryption involves alpha raised per k times mod p, and actually beta raised per k times mod p, but multiplied with plain text x. Okay, that is the encryption function. And the decryption function is defined as for y1 and y2 in ZP star, We define decryption function of y1 comma y2 as y2 times y1 raised to power a inverse mod p. So I leave this as an exercise for you to check that encryption and decryption functions are really inverses of each other, right? So you need to check that. I will give you an example anyway. So once you know the ciphertext is y1, y2, so if you want to find out, decrypt the message, right? So what you do, take y2 times y1 raised to power a. A was the secret, you remember? Inverse times mod p, right? Then that is nothing but your decryption method. So let me take an example. P is 2579. Prime is this. Alpha is 2. Order of alpha is p minus 1. So alpha is a primitive element. A is suppose 765. So beta is 2 raised to power 765 mod 2579, which is nothing but 949. And now Alice, suppose plain text X is 1299, a number like this. Okay. So Alice wants to send this thing to Bob. What she does? So she take a random number k 853. Random number, you remember, we need to take a random number k. Then she computes y1 is equal to 2 raised to power 853. Okay. Mod 579. It turns out to be 435. And y2 is equal to 1299 into, this is your x, plain text, times 949 raised to power 853. Okay. Beta raised to power k. This turns out to be 2396. So the Bob will receive ciphertext y1 comma y2. So Alice is sending this plain text. In order to send plain, she wants to send this plain text. She chooses a random number k, then computes y1 and y2 like this. So now she is sending this pair. Okay. So Bob receives ciphertext 435, 35 and 2396. This is your y1 comma y2, right? Then he computes plain text x as 2396 into 435 raised to power 765 inverse mod 2579. This turns out to be 1299 plain text as you want it, right? So I hope it is clear to you that so decryption was y2 times y1 raised to power a inverse. That's what we have done here. And to get the answer. Okay, so now this is so this algorithmic crypto system can be implemented in different kind of groups. The first group that is there, the multiplicative group of finite field. Are you aware of finite field? And the group of an elliptic curve. Or finite field. This is the finite field with p raised for n number of elements. I think in the beginning of the semester I talked about finite field, and also in the discrete class, if you remember. So from Z2 we constructed GF4, field with 4 number of elements. GF4 we constructed GF8 and so on, right? In general, for any prime P, we look at ZP, take a reducible polynomial which is not factorizable in the ground field, attach a root, right? And that's how we construct it. So basically, in general, we have field like f p raised power n. If q is p raised power n, so number of elements are p raised power n. Okay. So this will be constructed from GP, okay, integer modulo p, and then you build tower-like thing, right? So the collection of all finite field elements, okay, you basically, when we remember, if you remember, we used to make a table, multiplication table. So you accept 0, whatever is left forms a multiplicative group when you arrange in the table, okay. Okay, so that is how, if you remember, so that group can be used for building the algorithmic crypto system. See? So this is finite field is a very important idea. Similarly, another group is of elliptic. So what is elliptic curve? Elliptic curve. Are you familiar with parabola, hyperbola, ellipse, right? What is the basic property that you know about these curves? You can, or a circle even. So circle, you know that x square plus y square is equal to r square, right? This is the equation of the circle, right? Now, each of these equations have one very important property, that you can always find a parametric equation for the circle, right? X is equal to cos theta, x is equal to r cos theta, y is equal to r sin theta, right? Theta is a parameter, or t, whatever you want to use. Similarly, for hyperbola you can do, parabola you can do, all these curves that you have encountered till now, you can do the parameterization easily, right? There are curves for which parameterization is not possible. Okay. And so all these curves for which parameterization is possible, like circle, parabola, hyperbola, and all, and so on, or ellipse. So these are known as curves with genus 0. Genus is a measure. I'm not giving you the formula, but I'm just telling you, genus is a measure of smoothness of the curve. Okay. So all these basically curves that you can parameterize have genus 0. Now, there are curves with genus 1, more than 1, and so on. Curves with genus 1 are known as elliptic curve. Okay, elliptic curve. So you cannot find parameterization for curves. I'll give you an example. Okay. So actually, if you take these elliptic curves, you can, these curves have been defined over real numbers, complex numbers, and so on. So basically, you are solving these equations, these special kind of equations over these things. If you take the points on these elliptic curves, actually, and with respect to addition, they form a group. So if you take a point P on the elliptic curve, you add its P and take another point Q. So P plus Q will again belongs to the curve itself. Sum of 2 points. So there is a way how to define sum, which I am going to talk about in a minute. So this collection of points on the elliptic curve forms a group with respect to addition. And hence, we can build algorithmic crypto system on these curves. Okay. So we can take our, so basically we can talk about elliptic curves over reals or complex, but I'll start with reals or complex. But actually, in our crypto system, we use finite field. Either you define elliptic curve over finite field or integer modulo p. I'm going to give an example of integer modulo p, so that you can see how this system works actually. A very beautiful system. Most beautiful thing actually, elliptic curves. You will observe that. Okay. In fact, there was a big prize, So I think in calculus you might have heard about Riemann hypothesis, right? I don't know whether you heard about it. Riemann hypothesis, $1 million prize. मैंने तो calculus पढ़ाया नहीं, so then you don't know. So basically, Riemann hypothesis says that zeta z is equal to summation n is equal to 1 to infinity 1 over n raised to power z. This equation has all its roots on the line real part of z is equal to half. The proof is still not known. If you can prove it, you can get $1 million. Such an important problem. So, this has got connection to these points on the elliptic curves also. When we look at over finite fields, and there was a very famous bound known as Haswell Bound, where you compute how many points are there on a curve. It's a very nice bound, beautiful mathematics if you really want to understand, or enjoy mathematics, Otherwise, for crypto system, so elliptical crypto systems are quite useful because they have short keys for your credit card, or all these card-based systems and so on. They're quite useful. So these are pretty common things now. So during early 80s, people were developing them, and 80s, 90s, and so on. A lot more work was done. So curves for which genus is 1 are known as elliptic curves, and curves with genus greater than 1 are known as elliptic curves. Okay, hyperelliptic curve. Okay, so let me show you the beauty. I am going to talk about real case. So A and B are real numbers such that 4a cube plus 27b square is not equal to 0. Why this condition? It will be clear in a minute. Why do we need this condition? A and B are two real numbers such that 4a cube plus 27b square is not equal to 0. Okay. A non-singular elliptic curve I will call it as EC, right? Elliptic curve is the set of solutions x comma y in R square to the equation y square is equal to x cube plus ax plus b. Beautiful equation. Y square is equal to x cube plus ax plus b. This is the equation of the curve. X and y are points on the real numbers, right? I mean, these are real numbers. Okay. So basically, solution of this equation is any pair x comma y which satisfies this equation, right? In R square. So normally our task is to find these points x comma y. Okay. So now this is our elliptic curve. So I will tell you why that condition is there. Looks like very beautiful and simple thing, right? I think when you play with it and you try to find the roots, you will observe that. So basically, we also have a special point O known as point at infinity. So solution to this equation is also one special point known as point at infinity. I'll tell you about that later on. Let me give you one example before moving further. Okay, so example is y square is equal to x cube minus 4x. One, two, three, four, minus 1, minus 2, minus 3, minus 4. It is something like this. This is the graph if you plot it. Okay, so these are the points which are members. So here something like this loop is there and this kind of stuff is there. Okay, so these are, so basically we are looking for these points. So right now I have plotted out 4 reals, right? Of course, drawing these pictures for finite fields or the elliptic curves over integer modulo p is a difficult thing. You geometrically it is very difficult. For reals you can plot, as you know that because in the discrete math everything is discrete, right? So it's kind of difficult to imagine. Okay, so how it will look like. So this is the equation, okay? Now the equation, so as you know that our equation is y square is equal to x cube plus ax plus b, okay? So this equation x cube plus ax plus b is equal, x cube plus ax plus b is equal to 0 has three distinct roots if and only if 4a cube plus 27b square is not equal to 0. Okay. I think I can write it down again. If and only if 4a cube plus 27b square is not equal to 0. So this equation on the right hand side, x cube plus ax plus b is equal to 0, has three distinct roots if and only if this condition is satisfied. Okay. And when this happens, we say that elliptic curve is non-singular. If this value turns out to be 0, if 4a cube plus 27b square turns out to be 0, we say that the elliptic curve is singular elliptic curve. Okay. So it basically, these roots are important, okay, depending on what kind of roots you are going to get. You will get three distinct roots provided this condition is satisfied. And I want the distinct roots so that we can talk in terms of groups, okay. So I should just mention that if 4a cube plus 27b square is equal to 0, it is known as singular elliptic curve, okay. Okay. So now I'll take 1 minute break. Now what I'm going to show you. So you know the definition. So this condition is there. And we are looking for points x comma y on this equation, right? So basically now I'm going to show you how do you define addition of 2 points on this curve, okay? So in order to define addition of 2 points on this curve, what I'm going to do, so of course there are certain meanings, geometrical meanings of it. So basically I will show you how to define addition, and then I will solve for the equation actually, so one way is I can write down the formula, but you will not understand how this formula is coming. So I will give you some motivation about how the formula is coming for addition of 2 points on this curve. Once you know that, so then I can summarize 4 points. So basically you can verify easily that if you take any 2 points, P and Q on the curve, so P plus Q belongs to the curve, it's closed. Then P plus Q plus R is equal to P plus Q plus R, right? I mean, the associativity is there. There is existence of identity elements. So this point at infinity, O, which is very important. I have not shown you how this works. Point at infinity, O, works as an identity element. So P plus O is equal to O plus P is equal to P for every point P on this elliptic curve. Okay. And existence of inverse element. There is, so if there is a point P, there is a point P inverse such that P plus P inverse is equal to O. Okay. So these kind of properties are there in the elliptic curve. Now, okay. So So we are talking about non-singular elliptic curve. So I am going to look at now that E plus is an abelian group. One can show this. First thing, I just want to mention that there exists a point O, which is known as point at infinity. I have not described it, what exactly it is right now, but I'll just give you some motivation that P plus O is equal to O plus P is equal to P for every P in on E. Second, if P and Q are in E, So say P is of the form x1 comma y1 and Q is of the form x2 comma y2. How do you define addition? So basically I am going to make three cases. Case 1. So addition has to be defined depending upon three cases. The case 1 is when x1 is not equal to x2. Okay, x1 is not equal to x2. So the first coordinate. So P and Q are 2 points, right? So by the way, how the discrete log problem becomes here? Because if you take a point P here, because it is a group, all the points forms a group. So P, add P m times, P plus P plus P m times. So m times P is equal to another point Q on the curve. So m times P is equal to Q. P and Q are known, but m is not known. So actually m is a, so here everything is with respect to addition, right? The discrete log problem becomes, so m times P is equal to Q, where P and Q are known points on the curve and m is unknown. Okay, that is how it works. Okay. Okay, so we are ready to describe this. So I have to define addition of 2 points P and Q, where x1 is not equal to x2, that is given to us. So suppose L is a line through P and Q. L is a line passing through P and Q. So then what will happen? So actually, there is a property, I am not actually proving it, but I am just telling you, if P and Q are 2 points on the curve, and you draw a line by connecting P and Q, that line will intersect another point R prime on the curve. Third point, it will intersect on the curve. L is a line through P and Q. So L intersects in one another point R prime. Okay, now we reflect R prime in the x-axis. This is an important geometrical thing that we are doing. We get a point R. So our P plus Q is nothing but R. So let me tell you. So what we are saying, if x1 and x2 are two distinct points, I mean, so if P and Q are two points, right? And x1 is not equal to x2, this is the condition. In that case, if you draw a line L connecting 2 points P and Q, that line will intersect another point R prime on the curve. Okay. So that point R prime, we reflect R prime in the x-axis. We take the reflection of that point on the x-axis. Basically, we get a point R. So addition of 2 points P and Q will be P plus Q is equal to this point R. That is how the addition is defined. Okay. I've given you the geometrical thinking of it, but now actually I will do the calculations for you. So I will, you know that a line passing through 2 points, if we can write down the equation of the line, right? Coordinates are known, x1, y1, x2, y2, right? So I can do all those calculations for you to show you what happens there. So I want to find out the formula for the addition. I gave you geometrical meaning of the addition, right? 2 points P and Q intersect in the third point R prime on the curve. Okay, you reflect on the x-axis. That point, you become a point R. So P plus Q is equal to R. All these, whatever I have told you geometrically, I can now calculate. So formula is, so equation of line is, equation of L is y is equal to lambda x plus v, right? Mx plus c, whatever you write on. So lambda x plus v. So slope is lambda is equal to y2 minus y1 divided by x2 minus x1. That is the slope. You remember 2 points P and Q, x1, y1, x2, y2. And v is equal to, this intercept is y minus lambda times x1, same thing as y2 minus lambda times x2. That is our v, right? Everything makes sense. Now I have to find points in elliptic curve E intersection L. I want to find, now intersection I need to see, right? So points on the elliptic curve and the line that we are drawing, right? So that's why I have written E intersection L. What are the points which are common, right? So what we can do, that means we can substitute this value into the equation of the elliptic curve, right? Equation of the elliptic curve is y square is equal to x cube plus ax plus b. I can substitute this value y here. This will be lambda x plus v whole square is equal to x cube plus ax plus b. I can call it equation star. This gives us the value, a equation in x cube, in x actually. This plus a minus 2 lambda v x plus b minus v square is equal to 0. I mean, you're just raising it, simplifying it, and transferring on one side. So we get equation in x cube. Degree 3 equation in x. Now remember, x1 and x2 is known to us because those are the points on the curve, right? What I want to find the formula for third point. x3 and y3 I want to find a formula because p plus q is equal to some point r, so I want to find that what is the coordinates of r, okay? So basically, if x1 and x2 are distinct points, real points, you know that third point will also be real, right, for this root. If 2 points are real of a cubic equation, third point will also be real, right? So and we know that sum of the roots, if I apply the formula x1 plus x2 plus x3 is equal to minus times this quantity, right? So this is lambda square. Sum of the roots equal to minus b by a hota hai na formula, right? So x1 plus x2 plus x3 is equal to lambda square. Therefore, we have the value of x3 as lambda square minus x1 minus x2. Right? Now x3 is the coordinate of r prime. Remember our construction? So if P and Q are 2 points on the curve, we draw the line L which intersects third point r prime on the elliptic curve, right? R prime coordinate I have found x3. x3 I have found, the first coordinate I have found for r prime. So that means what is the coordinate for r, which is reflection along the x-axis? So I can find out what is the point. So basically, if y coordinate of r prime is minus y3, y coordinate of r is equal to y3, right? Now the slope lambda is determined by slope lambda by only 2 points on L. So I can find out, so if we take a point x1 comma y1 and other point x3 minus y3. So lambda is nothing but minus y3 minus y1 divided by x3 minus x1. Therefore, from here I can find out what is y3. Okay. Basically, so slope can be determined by only 2 points on the curve. So one point is this, second point on the curve is x3 comma minus y3, right? R prime means intersects, right? So slope is this, I can find out. So from here I can find out. So lambda is known to us, right? So we know that what is not known is y3. So y3 we can find it out, right? This is y1, yeah. So y3 is equal to this. So basically I have found a formula. I'm going to write it now. Formula is, so P plus Q is given as some point x3 comma y3 where, so of course this is the case when x1 is not equal to x2 So basically, we have x1 comma y1 plus x2 comma y2 is equal to x3 comma y3, a point on the curve such that x3 is equal to lambda square minus x1 minus x2, y3 is equal to lambda times x1 minus x3 minus y1, and lambda is equal to y2 minus y1 divided by x2 minus x1. So this is how we found the point on the curve, right? Got it? थोड़ा सा इंटेंस था ना, बट मॉर्निंग का टाइम है, थोड़ा सा लोगों को नींद भी आ रही होगी ना, सुबह सुबह नींद पूरी नहीं होती है, आई नो, बट ठीक है, आई थिंक so I think I will stop at this point, don't worry. Two more small cases I will do, and then I can give you an example of elliptic curve, over the finite field GP in the next class. And then, so then how to build the crypto system, because, right, so you know that algorithmic crypto system. So essentially I will write down those properties in the next class. So in the next class, we are going to do this elliptic curve business. We will finish. If possible, we can do the quiz also, right? Or maybe in the next class, we'll see. And then there are two more lectures left. We will talk about digital signatures, and I am going to talk about RSA signatures and algorithmic signatures. Probably two I should be able to cover. Okay. There are many, but I will not be able to do that. But I think that's all for the cryptography class. Of course, there are many things which are possible. It's a very large course, but this time I think we have less number of classes, right? Maybe anyway. So I think that's all. Thank you very much.